Tipo questo stream si deve accendere? No.
No, a posto così. Sì, tutto a posto. Chi il suo audio lo prendo da qua. Ok. Benvenuti a tutti, grazie per essere qui dopo una giornata di ufficio sicuramente non facile. E benvenuti a Localhost. Questo spazio è la sede dell'associazione Crafted Software, che come dice il nome, insomma, tratta temi legati all'ingegneria del software e soprattutto a quel software che consideriamo fatto bene con i valori della software craftsmanship. Localhost è uno spazio, diciamo, polifunzionale, perché qua dove siete adesso è la sala eventi, dove stiamo cercando di far partire la scena delle community a Milano, in città. Quindi oggi ci siete voi, settimana prossima ci sarà React GIS Milano e a volte ci siamo anche noi di Crafted Software. Mentre il piano di sopra è un ufficio condiviso dove di giorno lavoriamo, ma è aperto a tutti. Chi vuole venire a lavorare ci può contattare, insomma, chiedere informazioni. Puoi andare avanti alla prossima, grazie. Ti ringrazio. Infatti voglio ricordare che appunto i prossimi eventi che abbiamo programmato qui sono settimana prossima un link coffee su tema React.js organizzato dalla community di React.js. Poi il 31 marzo avremo con Fabrizio Wolfner un talk su Site Reliability Engineering. Fabrizio, eccoti qui. Il 7 aprile avremo in realtà il primo meetup di una community che si chiama Product Personas e sarà un meetup basato su Lightning Talks, quindi diciamo speech di un quarto d'ora circa al massimo, legati allo sviluppo del prodotto. Mentre il 13 aprile abbiamo già programmato, ma non abbiamo il tema, una sessione, diciamo, pratica su Test Driven Development. Posso chiederti la prossima? Grazie. Naturalmente mantenere questo posto per un'associazione senza scopo di lucro, quale siamo noi, non è facile. Potete sostenerci in vari modi. Alcuni di questi sono, ad esempio, indossando una maglietta come questa, oppure bevendo il vostro caffè dalla tazza, come esposta sopra, ma soprattutto dopo questo meetup, prima di andare a cena, se volete bervi una birra con noi, di sopra le abbiamo e le potete prendere. Oppure una donazione libera scrivendoci a info@craftedsoftware.org. L'ultimissima slide, poi ti lascio. Per chi non lo sapesse, noi come associazione facciamo anche corsi di formazione e anche quest'anno abbiamo lanciato un corso sui sistemi distribuiti che appunto si chiama Mastering Distributed Systems 2. Il docente sarà Mauro Sardienti, perché 2 l'anno scorso abbiamo fatto la prima edizione e quest'anno vogliamo proseguire, quindi non è una ripetizione, è un continuo del programma che abbiamo cominciato l'anno scorso. Sarà un workshop fatto in 5 appuntamenti online, quindi abbiamo deciso di fare questo formato, diciamo, non una giornata intera perché è molto pesante da seguire, diciamo, l'attenzione online è difficile da mantenere, quindi abbiamo deciso di spezzarlo in 5 appuntamenti di un'ora ciascuno. L'anno scorso è andata bene, il formato è stato apprezzato, lo vogliamo riproporre quest'anno. Per le community, per la community di Crafted in generale, abbiamo preparato uno sconto del 10% sul prezzo del biglietto, quindi potete andare sul nostro sito che è www.craftedsoftware.org, nel menu in alto c'è il link alla pagina dell'evento e poi su Eventbrite infine potete applicare questo sconto qui, crafted_community. In ogni caso, se volete maggiori informazioni scriveteci o mi fermate dopo, non c'è nessunissimo problema. Grazie mille per l'attenzione e lascio la parola a Dominik.
Okay. So we will switch to English because someone is not from Italy. Welcome back to Python Milano. We haven't been doing events for the last 2 years, so it's a great pleasure to have you here. What we do, we are a community that does quite some things in Milan.
Can you use the microphone?
Sorry. Okay, so Python Milano is a community that does quite some things. Our core activities are meetups. We have a meetup like this evening, which is a talk, which is in the evening for about an hour long. Then we had in the past some Python pills, so that are 3 small talks of 15 minutes each, one after the other. And in the past, we also had some workshops, which are a bit longer. So in future, we might also have these kind of events. We have some more informal Birra, so where there is no talk, just eat and drink together. We had a couple of them in the last months. And then we have a podcast, which is in Italian, which is about Python. We had already 16 episodes. We had also one guest here, where we run interviews to people around the Python community about coding, data science. So if you go to your podcast app and look for Intervista Pythonista, you will find it. Probably after this talk, we will go for an informal beer to eat and drink something. So if you want to join, you are more than welcome. We don't know yet where to go, but we will decide. Cesare?
Okay, next slide. Okay, our community has a lot of social social links. One is milano.python.it. Then there is Slack. The main channel for us is Slack. And I have to tell you that if you want to speak in our meetup, just connect to Slack to talk about it. We are not looking for super expert in Python. If you have a nice story to tell where Python is involved in some way, we are waiting for you. So it's not important. Python is important to see a nice story like Dominik will tell you in a bit. Then there is also a LinkedIn page, and we also have Twitter. And if you don't mind, if you give me the permission, I will take some photos to post on Twitter this night, if you agree. And there is also the link to our podcast, Intervista Pythonista, which is in Italian. And if you speak only English, you can stick with Michael Kennedy. And that's it.
All right, so thank you very much for the invitation. Or maybe I'll just flip it here. So can you hear me? I mean, online, hopefully. Okay, great. So again, thank you very much for the invitation to Python Milano. I'm very excited to be here tonight and to talk mainly about the results of my master's thesis, but which is an ongoing project, and to talk a bit about the background of geospatial Python in general, where I use Python in my everyday work life or also hobby life, and where it really comes in handy in geospatial programming. I'm Dominik Weckmüller, and I'm a GIS engineer and geodata scientist for the past years. And I'm really excited when it comes to spatial data, like might it be social media data, or might it be remote sensing related stuff, so satellite imagery and all that kind of stuff. I'm really into it. I really like everything about it. Okay, so I'd say let's get a quick overview of what I will talk about tonight. And I want to keep it really practical tonight. So I just plotted you a quick draft of the application that I will show to you. And I will just quickly illustrate the individual components that we see here. So at the first part will be about data mining, particularly about the API that Instagram uses in their application. And the second part is already about a map front end that will be covered in Folium, which is the leaflet port for Python. But then, of course, if you want to have a production-grade app, you need a nice server or a nice web framework. And of course, which is the core of everything for tonight, is a nice database. And in our case, it's the Hyperlog log database. That sounds really complicated, but I hope I will break it down to a minimum and will really simplify it for you so everyone in this room will hopefully understand it in the very end. Okay, so I would say let's just jump right in. And if you have a laptop or a mobile device or anything and you want to follow it or play with the demo while I speak, feel free to go on my webpage, which is geo.rocks, and then LBSN dashboard, which stands for Location-Based Social Network Dashboard. That's what the abbreviation LBSN stands for. And so let's jump right in. And maybe you ask yourself why there are these weird flowers and the trees and this very crazy looking emoji, but I will clarify it just in a minute. All right, so there we go. And that's a working prototype of the entire dashboard. So if you follow me, I think it should load just in a second, also on your device. And that's pretty much it. So if you go on geo.rocks and LBSN dashboard, you see the prototype. And this app is fueled by social media data. And not only Instagram that I mentioned already, but also Twitter and Flickr data of a time span between 2011 and 2020, so roughly 10 years. And all the data that is stored in my backend is around 700,000 posts, split up into tiny components. So I'm not even storing the original posts here, but I'm just working with individual atomic components. And what this means, I will show you in the very end when we talk about hyperlog, because then all will hopefully make sense when we combine all the different parts. But first of all, let's talk about the app itself. So what can it do and what do we see here? As I studied during my master's at the city of Bonn, which is the former capital of Germany, it's located in the west of Germany, and I thought, why not make an application that investigates the social media posts for the city? Actually, I also have a quite personal motivation for this dashboard, which was really a trivial occasion where I wanted to play some ping pong with some friends. And the city of Bonn doesn't offer any map. So me as a geographer, I'm always looking for maps and geospatial information, but they didn't provide any information for this. And maybe also because lots of those ping pong tables are semi-public, which means that they're located on school grounds that maybe you can't access in certain times. But anyway, I really wanted to know where I could find these ping pong tables. And I thought maybe some people, when they play ping pong, they tend to post something online because in the end, out of 100 people, if there's only one person posting something about it and I mine the information, I can just access it. And I can also put it on a map and in the end, just have the visualization where these ping pong tables are located. So let's give it a try and just look what the database will tell us if we select Tischtennis, which is the German word, or ping pong. So we just query both words in this case. And there we go. So we have 3 different layers in this case, which are one time the Instagram locations. Another one is a heat map displaying the amount of posts in this area. And the other one are so-called hex bins. But let's start with the easiest layer, which is a so-called heat map. And a heat map basically works in this way that the lighter the area is, the more posts are located in this very location. So if we look at these different spots, we see that there might be some table tennis or ping pong hotspots, whereas there is also areas where you can't find anything. Of course, this is a foresty area, and you barely will find a ping pong table in this area. So instead, let's look at the locations themselves and maybe untoggle them. And there we go. And that's pretty much the map that I wanted to have when I was a student playing some ping pong, because what we can see here is all the locations where people on either Twitter, Flickr, or on Instagram posted something about ping pong or table tennis in Bonn. And we can see it here on the map. So if I would like to play some ping pong, I would look at these locations. And of course, I needed to verify that those ones are not sports shops, because they might also sell like ping pong equipment, like these tiny balls and everything. But I don't want to go there, obviously, but I want to play it. So I should verify these locations. And if I zoom a bit closer, and maybe I just take this one here into account, I can see that OpenStreetMap tells me that this one here is a sport park. And I think it's quite likely that you will find some kind of ping pong table in a sports park. Or if you zoom somewhere else, just like here, for example, there's a church. So might be that this church has a ping pong table in some of these semi-public rooms or for entertainment purposes. And so those are all the locations that you could take a look at when you consider to play some ping pong. Obviously, there are also a lot of schools. So if you look here, for example, there are tons of locations. And Gesamtschule just means it's a school for children, and that's very likely that this school has a ping pong table here, because you can see all the different locations here. And if you click on them, you can see, okay, they all have, this one here has like 5 different posts, and that's very likely that you can find a ping pong table there. But in the end, it's not only for very trivial purposes like ping pong tables, but instead you can also track more interesting stuff. So for example, while I did this analysis as a geodata scientist, I also bumped into the phenomena, or into this social media phenomena of the cherry blossom, because you might know these very pinkish trees. They are very beautiful and very aesthetical. And if you look at them, maybe it comes to your mind to take a picture. And if you're an influencer on Instagram, it immediately comes to your mind to take a selfie with you and this beautiful tree, obviously. So I took a look at Bonn, particularly, and I wanted to find out where the cherry blossom clusters are. And if you zoom a little closer on the very center of Bonn, you can see beautifully that on this heat map, you see these 2 streets here, and they are very bright. And that's the reason, or the reason why is that here, you can even see it on this OpenStreetMap, that there are plenty of cherry trees located along the street. And that's something you can really easily tell via this application, that there are tons of people posting about these cherry trees in the center of Bonn, but also obviously in, for example, the Botanical Garden, or just in different other locations. So maybe you remember the cherry tree emoji that you saw beforehand, but there was also another one. So there was this, this crazy guy with long hair, and this one is Beethoven, because Beethoven was born in Bonn. And so because the city is very interested in the social media resonance of Beethoven, I also looked into it and how Beethoven got reflected online and also geospatially in the city center. And if again, we only take a look maybe this time at these hex bins, we can see some very interesting things. So first of all, what are hex bins? Hex bins are just hexagonal bins. So bins, you might know, bins are just some component that is binning up some information. So just clustering all the information that is located within this hexagon. And so the color that you can see here is basically reflecting the amount of posts in relation to each other. So the darker the hex bin you see here, the more posts are located within it. And if you zoom a little out, you can see that all of these hex bins are quite wide, which means that there are few posts about Beethoven there. However, if you zoom on the city center, you can clearly tell that there are 2 very darkish hex bins. And if we zoom a little in, I can immediately tell you why, because if I just deactivate this layer for a second, you can maybe see, I don't know whether it's too small, but there's written Ludwig van Beethoven, and that's a statue. So because in the city center of Bonn, there's a big statue of Ludwig van Beethoven, and obviously people tend to post about it because it's there. And the other big hex bin that we could see is actually darker, and it's located here. So we see around 2,000 posts about Beethoven here. And if we deactivate the hex bin layer again and zoom a little closer, maybe you can read it, maybe not. I just read it out loud. It's called the Beethoven House. And it's basically the birth house of Beethoven, which is nowadays a museum where you can go and just take a look at all the different, the setting of the house and everything. So this seems to attract really the social media attention for Beethoven in Bonn. And so combining all this data, suddenly you have a geospatial image of Beethoven in Bonn. And obviously you can use this app for many different other purposes. What I put here on this demo online is just a very small selection of things you could do with it. So for example, you could also look for volleyball spots, or for hotels, or for restaurants, or for example, when I studied in Bonn, I was looking also for Italian restaurants. So I just entered like Italiani, Italiane, Italiano, Italiano, and it just happened that Italians post about these Italian restaurants in Bonn, also in Italian. And that's the reason why I could really easily tell the Italian restaurants in Bonn, for example, or just if you enter Pizzeria, for example, you immediately get a nice map with an overview of all the different hotspots in your city. Okay, so enough of this app. So let's talk about what is happening here in the background. And this is hopefully going to be really interesting. And I will switch from my slides to the Jupyter notebooks, because it's just a very good way of visualizing some things and doing some live coding with you tonight. So let me just put it in full screen mode. No, maybe it doesn't want to. So maybe not this time. However, so let's start at the very beginning. And at the beginning of every app, of course, there must be some data. And in this case, like I told you already, the data comes from Instagram, Twitter, and Flickr. Flickr, on the one hand, is pretty open source, and you can just access the API directly. Twitter usually requires a developer account, which is also really restrictive, so you can't really mine that much. But there are some certain scrapers available, because most of the big social media platforms, they provide the data through a public API that you can still access to some degree, or you can always scrape the data, because those platforms usually put all their users' data public if you don't explicitly set it to private, because it also requires, obviously, attention on search engines such as Google. And so both engines, they display the results and also the actual posts. And Instagram, by the way, is the most interesting platform for geospatial purposes, because most of the posts on Instagram are tagged with a location ID. So if you ever posted something on Instagram, you might have had the occasion to tag some space, like some location, and those locations, they have a certain ID. And if you take a closer look, for example, I choose one of the streets in Bonn where we saw these beautiful cherry trees, which is the Maxstraße in Bonn. So you can see there's some nice tree and some nice cherry blossoms here, wonderful. And this location here, if you would like to explore it, it has this location ID. And if you just displayed this location, so let's just open it and take a look at it. If Chrome permits me to do it. Maybe it doesn't like to. However, this is a screenshot I took in advance. And the API basically works in the same way like the front end. And you can actually just request the API of Instagram by adding a question mark for the parameter, then __ a equals 1. And that's basically everything how you can mine Instagram. It's shockingly easy, in my opinion. And during the past years, Instagram added some features to make it even harder to access this API, because before you could access it completely free. But nowadays, of course, there are some limits to it. So if you request too much, like in every mining action, they will block your IP, and then you can't mine anything anymore. So the endpoint is just easily accessible. So let's just do it here and do it live and see whether it works this time. So I'm just using the normal requests package here with Python and just using some Jupyter plugin to display the JSON nicely, and we see that it worked. So I just queried this endpoint here, and I can see they use this GraphQL, and we can see the location nicely formatted. We see the name, that's the Maxstraße in Bonn, and we see some lat long. So some geospatial information. The coordinates are really important, and those locations that you can see here, they actually make part of my app. Hmm? Ah, okay, sure. Oh yeah, it's really small. So maybe a little more. Okay, so I hope that does it. Okay, so like I said, you can see that this location here is called the Maxstraße in Bonn, and it has a latitude and a longitude. This is the information, or a part of the information, that I'm displaying in my dashboard. So I just queried these locations and looked at the different posts that are registered or tagged with this location ID here. And if we scroll a little down, we see edge location to media. And if you take a look at it, there are 34 posts here. And if you take a look at the edges, you see a nice list with nodes. And if you click on it, you can see that those ones here, those are already the actual posts, and they have certain attributes here. And you can do plenty of different things with those parameters of these posts. But I'll just keep it that way and just keep it simple and say these posts are easily accessible. But of course, if you want to main it on a big scale, it's not working, because if I would fire like 5 requests, they would already block me. And as a student, of course, I didn't have a big budget for my thesis, but I still wanted to access the data for research purposes. And that's the reason why I came up with a very simple idea. So many companies, they mine this data already via costly VPN networks, but there's actually a really big VPN network available for free, and it's the Tor network, if you heard of it already. And you can actually just use it. So you just, or in my case, I just used the TorPy package, which is just a port for the Tor network. And you can just fire the requests in just the same way. So let's just try it live and see whether it works, or whether this node was already blocked. And I'm just connecting to the Tor network, and we see it already worked. So we got our JSON result here, and we just queried the Instagram API via Tor. And you can imagine, as there are like thousands of Tor nodes available online nowadays in the world, you can use plenty of them also in parallel if you would like to mine these data. And that's actually what I did in one of my tools. So it's fast Instagram scraper. Scraper is actually misleading because it's not scraping, it's just querying the API, and it's doing this for you. So if you want to give it a try and just take a look at the data, feel free to use it. And it's just doing everything really conveniently and also in parallel. So why using Tor to download some data? I use this to fuel a front end, of course, because in the end, I wanted to display all the spatial data that I had and create a value for the people, because that's in the end the very idea that is behind all this, or my thesis and all this project, that all the data that there is available online nowadays of these different social media platforms actually belongs to the users, because they produce these data. However, the big companies like Facebook or TikTok or any other of these companies, they hold a monopoly on this data, and they don't provide any of these data usually to the public. Maybe they have some kind of partners that they work with, or they offer some developer accounts that are really limited, but you can't really access all the data on a big scale. But just imagine, also keeping in mind maybe the dashboard that I showed you already, the potential that you had if you had access to all the data, and also to the spatial potential, because you could investigate really easily how a city is developing, what kind of hashtags are important for a city. Maybe a city like Bonn, for example, they launched a hashtag like BTHVN for Beethoven, just fancier. And you could easily investigate how people interact with it online, like which locations are actually like, or are in resonance with this hashtag, and do people actually use this hashtag? In the case of Bonn, this was not so much the case. So we found out that people don't really use this hashtag so much. And that's really valuable feedback, because the city can then react and change something, or maybe do some different advertising to maybe a target group that is potentially younger than 60 probably. But you have some feedback that beforehand you couldn't. And you didn't have any geospatial feedback on this end. So if we just go to the second part of the whole app, let's go to the map front end, because actually this is already enough to produce something visible. So just querying the location of Instagram and then putting it in a front end, we can just very conveniently use leaflet and the respective port to Python, which is called Folium, and just create a very simple HTML map here. And the main lines that we need are just these 2 lines. So we just plot a beautiful map and 2 lines of code, basically, because what I'm doing here is I'm just getting the JSON ready, and here just creating a nice pop-up. And if we executed it, so let's just do it live, we see that there's the city of Bonn. We have an interactive web map, and if we click on this marker, we see, voila, we see the location ID and the name of the location, which is the Maxstraße in Bonn. At this point, we could already add some of the post information to this marker if we wanted to, but this is just to visualize how this works in a very simplified manner. And obviously, later on, I want to show you why I don't want to work with the original data and don't want to store it in a database, because I don't want to put the privacy of the users at risk, obviously. And that's the reason why I don't want to store the original data, but rather use a different algorithm that we will take a look at later to put it in different parts. But let's take a look at the third component, which could be a server, and let's say some geospatial processing. So if we had mined some data and we had a dashboard already, let's take a look at how you could process this data. And here, I know it sounds a bit cheesy, but GeoPandas is really the Swiss knife for geospatial Python. I use it almost every day. It's very convenient, and it's basically just a plugin on Pandas to work with geospatial data. So if you know Pandas, if you ever worked with it, it's a really convenient package to work with data, to filter it and to convert it to different export formats like CSV or JSON or HTML or even Markdown or whatever. And it's just really convenient to work with it. And GeoPandas just adds the geospatial functionality, which is not so trivial because in geospatial, you're working with different map projections. You have just different characteristics. You should choose the right projection for the right area of interest. And it's not as easy as it seems. It's just filtering that long. So there's a lot more behind it. So if, for example, we assume that we had some data, like in my case here, I just have plain CSV in this case, and I just read it with Pandas in just one line of code. And we have a beautiful Pandas data frame with lat long, some information about users, posts, and user days here. And we also have some strings. So this is some string content that users posted on these locations. But please note that those ones here are not only Instagram locations, but also Twitter and Flickr locations, just with lat long in this case. So if we wanted to open, or if we wanted to just open a geo data frame in this case, we could just use the Pandas data frame here and just tell GeoPandas that we have a geometry column that consists of this lat and long. And that's basically everything. So we just hand it over to GeoPandas, and there we go. We have a geometry here that is based on the points that we saw beforehand. And there's just one more thing I didn't tell you, and that's this code here, this EPSG code. And this is a so-called coordinate reference system. And it tells you basically how to interpret the coordinates that are handed over in this case. Because usually different applications use different projections for different purposes. All of us, we are very used to the web Mercator. That's the projection that also Google Maps uses. So everything looks really familiar. But there are also tons of other projections that can look really distorted or can deform geometries. And that's only the reason why I need to tell GeoPandas that I'm using this particular coordinate reference system in this case. And if now I wanted to filter the data, it's actually really easy. But first, let's take a look at something that happens to everyone working with data. Let's just plot it really fast with the integrated plotting function. And we see that we have some kind of rectangle over there and one point down here. And points far away from clusters usually means that you have some kind of outlier. And you want to, of course, to get rid of this outlier. And how we do this is just by filtering the geodata frame by our area of interest. So let's say we're not interested in all of the data in Bonn, maybe that's too much, but we just wanted to take a look at a certain custom-defined area of interest, like in our case. And I really got used to the geoman.io JavaScript framework, which is really handy and produces instantly some GeoJSON for you. So my iframe here is slightly too big. And there we go. So if we entered just Bonn, by the way, this is an iframe. I'm just loading into the Jupyter notebook and interacting with the web page here, if you didn't see it before. And I really like it because you can just click on some icon here. Let's say we wanted to draw a custom polygon. And let's say we're interested only in some areas that are close to the riverside. And this would be our custom polygon. Then what geoman.io does is it just gives me an instant GeoJSON here. And GeoJSON is nothing else but a very normal JSON, but with a certain typology of geometry. So here we defined that this one here is a polygon that we drew, and it consists of certain points here in this case. And what I do, I just copy and paste it and use it to filter my data frame. So I could just easily plug it into a variable here and load it into a different geodata frame. So now we had one data frame here that is loaded, if you can see it. And what we can do now, we just filter our main data frame with all our data by this custom polygon that we just drew. And that's also just one line of code that you can see here, because GeoPanas has a functionality that is called Spatial Join. So technically, we're not filtering the data, but we're joining it. But because I just created one polygon, there's not much to join. There are no attributes to this geometry. And so the join equals, let's say, some clipping functionality. And so if we do it, it's also really fast and convenient. This would just lead to a geodata frame that is filtered. So if we looked here at the left column in the index, we see that some are missing here and that we have now around 1,000 rows in comparison to the around 40,000 rows that we had in the very beginning. And if we plotted it just really fast, we would see, okay, it pretty much looks good. It looks like the area that I drew before, and this works really conveniently. And just to give you a very brief overview of what GeoPanas is capable of, let's take a look at some real-life application that I recently Right, test, can you hear me? Okay, great. So what I did here is just program a very simple API. And this one is working here in this way. Let's just query it. really fast. That in this case, it just outputs a JSON, or you know what, let's just head over to Firefox because it has an integrated JSON formatter, so it looks way better. So here we go. And we see that the API, just based on GeoPandas and one simple command, outputs all the data to a very convenient JSON that you can now query and that you can do things with it. Or you can even look at a map, which is also just 2 lines of code if you want to take a look at it. And in this case, it's just, it has an included limit of 10 results. So let's say we have, for example, 1,000 results. This will take a little longer, but there we go. And we have plenty of locations here right next to Bonn that we can click on and see some information about it. And just this API just serves as a very quick illustration what you can do with GeoPandas in this case, and with just very few lines of code, which is, I think, really impressive, because if we scroll down here, I defined different outputs. So for example, if you wanted to convert your data frame to a CSV or to string or JSON or HTML, it's just 1 line of code. So there's a functionality already to it. And if you wanted to do the same with just Postgres, for example, or the usual database, this would take much more work and more lines of code, I'm certain. And this is just to illustrate like how easy it is to program an API with GeoPandas and with GeoPandas combined with fast API on this side. All right, so let's jump to the very core of what I wanted to present to you tonight, which is the so-called hyperlog algorithm. And for this one, if you want to follow it or read about it afterwards, I wrote a more detailed tutorial about it. So if you want to scan this QR code or just go on my blog, it's under geo.rocks post hyperlog. There I wrote a more detailed description of what hyperlog is and what it serves for and just how it works. Because obviously in a limited time, I can't tell you everything about it, but my aim is to provide you the foundations of understanding for hyperlog in this case. So let's start with a very, very simple experiment. And maybe you heard about it. If not, I will just refresh your memories. And it's the classical Laplace experiment, if you ever heard about it. So Laplace was a mathematician, and the probability of flipping a coin is usually just 50%. If you ignore the edge, then the coin can also land on the table like this. Let's just ignore it for now and assume that this coin will always fall either on heads or tails in this case. And let's talk about a simple bet. So if I told you that I flip the coin 2 times, like 1, okay, and another time, who of you would bet against me that the coin will land 2 times on the €1 side? Because if it landed 2 times on €1, you would get this 0. But if we repeated this experiment for a very long or plenty of times, the odds would be very bad for you, because we just said that the probability of this event is always 50%, and the probability of the 50% times 50% equals to 25% is very unlikely. So in 75% of the cases, I would win, and you in this case would lose money against me. And obviously, because we are Python programmers, I just set up a very simple script that is doing this experiment for us. And let's just take a look what happens if we flip the coin. So in this case, oh, unfortunate, you lose. And if we repeat it, you lose again. What a pity. And that's very congruent to what I expected to happen. So 3 times you lose, maybe 1 time. Oh, that's just a perfect distribution in this case, which I promise I didn't program. This is all completely random. Trust me, I imported random here. And this is really pretty much like the perfect result, that out of 4 times, 3 times you lose and 1 time you win. Okay, so far so good. But what does it have to do with hyperlog? We will get there in a minute. So I just want to prove to you that if we repeated this experiment for 100,000 times in a row, that the probability really is approximately 25%. So let's just Python do the thing again, and we see it outputs, if it's big enough in this case, yeah, it's roughly 25%, in this case, 24.9%. So we can assume, or it's safe to assume, that this will also happen in other cases. So just to sum it up, the probability for this event to happen, that we see 2 times 1 0, is 25%. And also, obviously, the other side of the coin is just the same probability. If we saw 2 times the 0 on my fake euro coin, or on the Italian coin, for example, it's also 25%. Okay, so let's add a level of complexity to the whole thing, and just assume that we had a longer experiment. So if we didn't toss the coin for only 2 times, but 6 times each, and we would write down the results. So if it was a 1 or a 0, we would have a list of events that you can see here, and I'll make it a bit bigger for you that you can see better. There we go. So it's, for example, 0, 1, 0, 0, 1, 0, and that should be completely random, right? And the length of this array in this case is 15. So what we can do now is we can take a look at the unlikeliest event that just occurred in this set. So if we just go back, we can take a look at it and, for example, take a look at only the leading zeros. And if we looked at the first event, there's only 1 leading 0. The second one has 0, but the third element already has 4 leading zeros. And if you remember, the probability for this event to happen is not so likely. In fact, it's 0.5 times 0.5 times 0.5 times 0.5, or in other words, 0.5 to the power of 4 in this case. So we could have an approximate estimate based on this number very soon, because we could guess based on this number how many times most likely you repeated this experiment of flipping the coin 6 times. Because if it was me to guess, and you only told me that you saw 1 time 4 leading zeros, I would guess, okay, this event is not so likely to occur. And because it's not so likely, I just make a quick approximation of the probability. And this is exactly what I told before, that we have 0.5 to the power of 4 in this case. And so I would guess that you flip the coin 16 times. This would be my estimate in this case. And that's already the very core of hyperlog log, that based on one information or one very tiny information out of a big set of information, we can guess the number of distinct elements in a set. That might sound complicated, but we will simplify it further in a moment. And so just to sum it up, this is really where the magic happens. So if we had a function that just returned us the unlikeliest event, like in this case, this is indeed a mockup function, we can guess the number of the experiment runs in this case. So if we would take it to the next level and take a look at this complicated diagram that is actually quite simple, because it just reflects what I told you. Because take a look at these events that we see here, a lot of 1s and a lot of 0s. So what we can see here is there is no leading 0. There's 1 leading 0, and the number is growing. So if, for example, we saw 7 leading 0s, that is reflected here, we could assume that the probability for this event to happen is below 1%. So it's really unlikely. And obviously, to achieve this number of zeros, you would need to flip the coin a lot of times. In fact, I would guess 2 to the power of 7, 128 times. So using this table, we can already take a look at a real-world implementation. And just keep in mind that by looking only at the leading number of zeros, we can determine a very long list of elements. And in fact, the statistics here are that you can fit 1 billion elements and 1.5 kilobytes of memory. And if you ever worked with 1 billion strings, for example, you know that the size of this data is huge. And this cardinality estimator, this is what hyperlog is, produces an error of around 2 to the 4%, which is really amazing considering that you can fit it in only 1.5 kilobytes here. If you want to read about it further, just take a look at the original paper of Flageolet et al. Those were the French scientists that developed this algorithm and also modified it a little bit that it's more accurate. But let's take a look at what happens if we didn't talk about coins anymore, but about some real-world application. So if we, for example, converted strings to their binary representation, for example, hello world, if we convert it in Python, it would be this long number of ones and zeros. All right, so if now we programmed a real-world application based on all this, how could it look like? We would start with a very simple variable, and this is nothing else here, with so-called maximum number of leading zeros. And you start obviously with 0, because you saw 0 leading zeros. However, if, for example, you had a server and you would monitor the different IPs that you see for the different requests that people fire on your server, you would see different IPs, and if you convert all of them to binary, you would have very different strings of ones and zeros. And so what we could do here is we just looked at the number of leading zeros for every bit representation of the IP, and if it's bigger than what is already in the set, we update it. If not, nothing happens. So the probability to see more leading zeros over a long period of time rises, of course, because at some point it will happen that one IP address maybe, if you hash it as well, will produce like 10 leading zeros, for example. And in this case, we have a really cool estimate of the number of distinct IPs that we saw, because in this case, if we would guess, this would just be 2 to the power of the leading zeros that we saw, 10, for example. If we saw 10 leading zeros, this would mean we have like 1,000 different elements in the set. All right, and this is just at the very core what Facebook and Google already did. They used this hyperlog algorithm to determine exactly this, and also for another reason. So just imagine you had 3 different servers, like distributed all over the world, and you wanted to get the number of distinct IP addresses that accessed your server. How would you do this? So either you would need to put in a big pot all of these IP addresses and run over it a cardinality algorithm, or you would just combine these different sets and have a different output. So if every server just documented the number of leading zeros that it saw, and you would only look at the biggest number, for example, one server saw 5, one saw 8, and the other one saw 10, then 10 is the number of the approximate number of different IP addresses that you saw. And you might already guess that this is quite inaccurate if you only take a look at the leading zeros, because in reality it's slightly more complex, and you bin these binary representations into so-called buckets or registers. There are different words for it, but it just makes it more accurate. Still, the functionality is exactly the same. And so this is what I did also in this application that you saw. So instead of just storing the original JSONs with the post data, I used this HLL database that was programmed by Dunkel et al. And using this package, we split up the posts into their atomic components. And I call it atomic components because posts consists of, for example, locations, of text information, of, let's say, origins like Facebook or Twitter or whatever, and of locations. So we had all these different components, and for every individual component, we could store individual HLL sets. So if we queried, for example, only the term tree, we would see a very, we would have the number of leading zeros, for example, 7, and then we could guess how many users posted something containing the word tree. So 2 to the power of 7 would then lead to a certain number in this case. And it's, like I said, it gets a little more complicated with so-called registers, but I think I will just skip it here. And by the way, afterwards, I will provide these notebooks and just put it online if you want to take a look at it further, or you can also take a look at this at this illustration here on the original literature on it or in my hyperlog tutorial. So, and that's basically the core of all this application that we have now in this app. And so this app doesn't need to store the original data, but instead just uses these hyperlog sets to combine the data, and it has very good features for privacy, because if an attacker could obtain all the HLS sets, the attacker could never, ever recombine all the data to reproduce the original posts. Because if you think about that, you were at a certain time, at a certain location, this would be that's very critical for privacy, because someone could prove that you were somewhere, or this might lead you into some trouble. Instead, if you split up all the components and you have different HLL sets, you can't recombine them because they're just independent of each other. And that's the reason why it's really convenient to use this hyperlog algorithm. And if afterwards you want to know something more about it, because I just put it in very simple words, just go on this page. I linked all the different GitHub repositories here and also some tutorial videos. So just give it a look if you like, or just ask me directly. And I think that's it for now. And I would then go to the Q&A section. So if you have questions, feel free to ask them now. I hope it wasn't overwhelming. And I'm very glad to re-explain something if you want to. Sure.
I think I understood more or less the algorithm to understand what is the name, what is the number of different users. But as far as I understood, this works very well with a huge number of posts. But the week before we saw just maybe few posts, 5 posts.
That's right.
So is it the same algorithm, or so it works also with that number?
That's actually a very good question, because indeed that's one of the weaknesses of the hyperlog algorithm, that with very little amount of data, its performance is very decreasing. Because if you imagine, and if you stick to the example that I gave to you, if, for example, you toss the coin 10 times, and 10 times in a row it lands on 1, it's very unlikely. But if it happens, my estimate would be horrible. It would be terribly wrong, and this is what can happen, of course. And to avoid these extreme outliers, the hyperlog algorithm has these so-called registers. And this is something that we can see here, these buckets. So just assume that this one here is the hash of one IP address. And instead of looking at the whole number of leading zeros, we split it up into tiny buckets of 4, like just 4 characters. And we look at each of these buckets individually. And then we just combine it via a certain algorithm that is also developed by Flageolet et al., by the way. But this one reduces the amount of error drastically, but also increases the memory, because, of course, we need to keep more sets for the individual buckets. So we could reduce the amount of buckets, we could increase the amount of buckets to a maximum, but then the storage would become really big. Or if we lower the amount of buckets, the estimate becomes just worse in this case, for example. But that's a really good question, actually. And you can set it to different register widths. That's what we do here, for example, with a width of 4. And by the way, maybe I didn't mention yet how you combine these hyperlog sets, but the way you do it is just you pick a location. For example, a location idea of Instagram. For example, the Maxstraße, the nice street with the cherry blossoms. And you take this ID of the location. And for this ID, we create the hyperlog set. So which is nothing else but the leading number of zeros in very simplified words. And we need a unique identifier of the users, obviously. And this is mostly some kind of ID, some kind of email address, or even a phone number or something. And with this idea, this one is first, like in this workflow, it's hashed and also cryptically hashed, and then split up or converted to this binary representation. And then it will be used by this algorithm to determine the leading zeros. And so you couldn't go the step back to original ID. This is just impossible. And that's the reason why it's very good for privacy. Still, it's not privacy preserving, but it's privacy aware, which is a big difference, because privacy preserving would mean that you couldn't retrieve any information about an individual user from this database. Instead, privacy aware is just a definition that we use for mentioning that it's really hard to extract any information about the users, but it would be possible. And I can make you a very quick example. Let's imagine we had 10 leading zeros in our set. And then maybe you have a user with 9 leading zeros, and you add it to the set. Nothing will change and nothing will happen. So your information gain is 0. Instead, if you added one user that accidentally had 11 leading zeros, the number would rise from 10 to 11, and you would have the information, okay, this user was not in this set before. It hasn't been seen. And this is the reason why you can still retrieve some information about these, or you could retrieve some information about the users, but there are also certain strategies to mitigate these risks. And it's the privacy topic about hyperlog is a bit more complex, and I think there's not enough time to go too much into detail, but still it's a really good way to avoid reconstructing the original data, because this is really impossible. Okay.
Question about geopartners. With your experience, how much you can stretch geopartners to run query on larger amount of data, and when do you actually need to switch to a specialized geospatial database?
Yeah, I mean, that's a good question. And in my experience, I used it in my geodata science work with data sets of around a couple of million features already. And this was quite performant still. In fact, it claims that it's on par with PostGIS, which is the plugin for Postgres with querying. So this is really performant. However, it's not so convenient that, for example, for parallel usage. So a proper database like Postgres would always be better in production. But still, if you just would like to create a very simple API, GeoPandas is brilliant. And in my opinion, GeoPandas is more for the data sciencey part than for real production. But it's really great, and it's also compatible with PostGIS, for example, because you could plug it into PostGIS. For example, if we would load a geodata frame from PostGIS, and then just do the queries with it, or just use it to transform the data to JSON, to CSV, to text, to Markdown, or whatever. This would be also some thinkable way of interacting with it. But that's a good question. So I would always, for big scale or for large data sets, prefer PostGIS.
Maybe one question
Sure.
In the space. Have you ever thought to process the image instead of just process the text? Because at the moment, you use the keywords inside the post, and I think a lot of posts nowadays are just images. So have you ever thought to expand your application?
That's a really good idea. And I also had this idea in the very beginning, but there's a lot of cons against this. So the first con is obviously that plenty of users that post something online are not aware of what the information tells about you. So they wouldn't expect that someone could actually download the data, perform some analysis with it, and maybe do some intersections with other data sets, and then maybe use it against you. And that's probably like most of the users nowadays, and it's safe to assume that you should be really careful when using these data sets. In fact, there was a case when some company used, for example, the Flickr data set, which is open source, and used it to train a machine learning model. And the bad thing about it is that you could assure that your picture was in the model, that it was trained with it. And that's very detrimental for privacy. So personally, I wouldn't use the images, but I could think of ways of still using it, because one amazing way is, for example, is the so-called accessibility captions, if you ever heard of it. It's just a tag when, for example, an image can't be loaded, or when you have maybe visually impaired people that can't see well. There are certain descriptions for these pictures, and those ones are already generated automatically by these deep learning models of Google or whatever company, and they're tagged with this. So, for example, for this simple picture that we saw in the beginning here of our trees, for example, there would be an accessibility caption, probably of, let's just have a look. There we go. Of probably maybe multiple trees in a street surrounded by houses. This is more or less what these titles sound like. So it's still like a human phrase, let's say, but it's always follows a certain structure. So house, some nouns like house, tree, and yeah, other nouns. And those information could very well be processed. So I thought about it, but the main reason I didn't is because it's not in the API. So I can't access it as easily as I can retrieve the other data. So I would need to look at each individual post to retrieve this accessibility caption, but I can't. By the way, there are also really interesting endpoints in the Instagram API. For example, they have some kind of like fake news score, whether this is like certified information and those kind of things. And this would be also really interesting information if you think about the possibilities using this and also referencing it geospatially. For example, where maybe you have a high amount of fake news that is received. For example, during the US elections in America, we saw a huge amount of maybe influence and also yeah, some fake news. Maybe the score would have been quite high. So this is also a thinkable way of doing it, of course. And by the way, maybe one more thing, one more word to this image thing. Assuming that users post stuff that they might regret in a couple of years, even though it's public, it doesn't give you the right as a researcher to use this information to whatever extent, obviously, because if this user would, for example, delete his tweet or his post on Instagram or whatever, you would still have a copy if you download the original data. And this is a reason why with Hyperlog we avoid this, and instead we do something that is called in-memory processing. So you can just imagine that while I'm requesting the data, it's saved in my RAM, for example, and while it's there, I immediately process it with the algorithm and put it or split it up into these atomic components like location, terms, and hashtags and whatever. And so I don't even need to store it on my hard disk. So it's actually all in memory, and there's no risk for the individual post to be saved, and also for privacy later on. By the way, if you want to have a look at the actual Postgres database that is running there in the background, this is the way you can query it. So you just select something, and the critical part here is what you can see here, by the way, because we perform this union here. And this is what I told you before. Imagine you had like different servers, like 3 different servers, and they all had their individual HLL sets. Then with this union, you can just combine them and get a very good estimation of the combined distinct elements that are occurring in this HLL set, by the way. And if we fire this request, just limiting it to 10, it's also quite performant, and adding some geospatial filters or whatever, you can all do it just with SQL here, and you get your results that you can then just put in your front end, and you can digest the information.
More questions?
Mm-hmm.
Thanks, Dominik.
Okay, thank you very much.